Hello and welcome. The topic of this video will be linear regression. This is a very important topic. In fact, this is where all undergraduate classes in statistics typically end, and where all the graduate classes in econometrics begin. So it's a very important topic, and it's a prerequisite topic for the rest of the class. So I suggest that you watch this video first before you watch any of my other videos. In this video, I will first provide a few examples of linear regression. Then I will talk about the linear regression model and the estimated regression line and the differences between them, and about predicted values and residuals. I will also describe the difference between single versus multiple regression models. Then we will talk about the coefficients and marginal effects, how to calculate them, about the goodness of fit, or the R-squared and adjusted R-squared, and we will conclude with hypothesis testing for the coefficient significance, whether we have a T-test for a single coefficient significance or an F-test for a joint significance of all the coefficients. So let me provide a few examples when we can use linear regression. The first one is if we would like to explain student grades depending on the number of hours that are studied. So hopefully we're expecting a positive relationship. The more hours you study, the higher the grades. Next example is the effect of education on income. Again, a positive relationship between education and income. We're expecting to see that. Next example is to study the effects of the number of bedrooms on house prices. And again, positive relationship here. More bedrooms would probably be associated with higher house prices, all else equal. And finally, an example of studying the effect of recession on stock prices. Here we would expect a negative relationship, where during recession stock prices are expected to be lower. So in these cases we use linear regression. So let me describe a little bit the setup on how to do linear regression. The most important thing to remember here is that regression analysis does not establish a cause and effect relationship, just that there is a relationship or a correlation or causation. So for example, if you regress, say, stock prices on whether or not we have sunny weather, and well, it turns out that there is a positive correlation, but you can't say that sunny weather causes necessarily stock prices. So the cause and effect relationship must be determined using a theoretical model or logical reason. And this is a hypothesis that that's how the variables would be related. So in regression analysis, the dependent variable must be a continuous variable, and the independent variables could be anything. They could be continuous or discrete or indicator variables. Anything goes, or a combination of them. The difference between simple and multiple regression is that in the simple regression we have only one independent variable, and in the multiple linear regression model we have two or more independent variables. Typically, if you publish in paper or something like that, most everyone uses multiple linear regressions. It's very unusual to find only one independent variable, but it's a good starting point, and we can look at very nice graphs on the next slides. Another thing to notice here is that we always have one dependent variable, right? The multiple variables only refer to the independent variables. So the linear regression model describes how the dependent variable is related to the independent variables and the error term. So the first equation that I have here is the equation for a simple linear regression. We have y is the dependent variable equals beta 0. This is a parameter or an intercept, plus beta 1, this is another parameter or a slope, and x1 is an independent variable, plus u is the error term or disturbance, and sometimes it's denoted by E as well. So this is a simple linear regression because we only have one independent variable x1. Or in the more general case, we can use matrix notation by saying y equals x prime beta plus u, where x is a matrix and beta is a vector of all the coefficients, of all the parameters that we have here. So again, this is the same as this, only a more generic version. So y is the dependent variable. We also can call this the explained, the predicted, or the response variable. X are the independent variable. We also call these control variables or regressors. And beta are the unknown parameters to be estimated. We don't know what these are, but we're looking for a relationship there. And in the specific case where we have only one independent variable, beta 0 would be the intercept and beta 1 would be the slope. And u again is the error term. So once we have the regression model, this is the estimated regression equation, which shows how to calculate the predicted values of the dependent variable using the values of the independent variable. So here we have y hat equals beta 0 equals, b0 plus b1 x1, and it's equal to x prime b. So notice actually three differences from the equation that we had before. First of all, we don't have y, the actual values of the variable. We have y hat, the predicted values. Second, these beta parameters that we had before and we don't know, we've estimated them, and they're b0 and b1. These are the coefficients that we have estimated. And notice another thing is that we don't have an error term here. There's no plus u because we cannot predict the value of the error. We can only predict the dependent variable based on the independent variables as well as the coefficients that we're estimating here. So the way we would interpret these coefficients, say this b1 coefficient, is that a 1 unit increase in x would increase the dependent variable y by b1 units. Okay? So this is the interpretation of the coefficients. So the regression residuals are calculated as the difference between the actual and predicted values of the dependent variable. So u would be equal to y minus y hat. Y is the actual value of the dependent variable. This is what comes to you in the data set. Y hat is the predicted value after you estimate the model and you plug the coefficients in the equation above, you can get these predicted values. And this is y minus, I'm replacing y hat with the expression that we have above right here, or in matrix notation we have y minus x prime beta. So these would be residuals, and sometimes it's important to check them and see how they look. So let me give you a few very simple examples of linear regression line. So here's the easiest example that I have. X would be our independent variable, and that would be the number of credit cards, and Y would be the dollars spent. And we're plotting here, that's a scatter plot of X versus Y. And I picked numbers that are perfectly on a straight line. It doesn't have to be, and real life isn't like that, isn't a perfect line like that. But here we have, when someone has one credit card, they have $100 in spending. When they have two cards, they have $200 in spending. When they have three, they have $300, and so on. So notice that if we have one credit card with 100 spending and two with 200, what we can say is that when we go from 1 to 2, or when we have a 1 unit increase in X, we have 100 units increase in Y. And this is from 100 to 200. So for each additional credit card, a person spends $100 more. This is what we call the slope of this line. So the equation for this line would be y hat equals b0 plus b1 x1, or it would be 0 plus 100 times x1. So notice that the intercept, or b0, is equal to 0. If you put a line in connecting those dots, it will hit right here. So that's why when x1 is equal to 0, y would be equal to beta 0, to b0, or that would be a 0 in our case. The slope b1 would be equal to 100. So when x increases 1 unit from here to here, y hat would increase by b1. So it will increase by 100 units here. So again, this is a very simple example of a simple linear regression. So let's complicate things a little bit, and we have another regression line. This is a new example, but we have a positive intercept. So now we have a line that would hit 0 at 400 here for y. So when x is equal to 0, y would be equal to 400. So the equation for this line is y hat equals 400 plus 100 times x1. So notice how we are going to interpret the slope here is that for each additional credit card that we have from 1 to 2, a person would spend $100 more. So notice that the slope of this line did not change. Only the intercept changed. So the 400 changed here, but the 100 did not change. So the interpretation of this coefficient is exactly the same. Okay, so now we will discuss regression error. So we're trying to make a prediction, and we're trying to make the best possible prediction for the y variable, for the dependent variable. If we don't know anything about the x variables, our best prediction would be this line here, which would be y bar, or the average for y. So just take all the values for the y, the dependent variable, the actual values, and you just take the average of them. So if you don't know anything else, that is the best prediction of y, of what y would be, the average. Okay, if now we have x variables that are helping explain this y variable, we can do better than just having the average value of y. What we can do is we can run a regression line through all the data points that kind of gets as close as possible to as many points as possible. And this will be the regression line. And the predicted values here would be on the regression line. It's the error that we cannot predict. So if this red dot here, if that's the actual value for y, this is what came with the data, y hat would be the predicted value of y, or this is what comes after we perform regression analysis. This difference here between the actual and the predicted value would be the error, or the residual, and that would be y minus y hat. We talked about that before. So this is the error. This is what we cannot explain by the model, but this difference here is what we can explain with the model. So if we didn't have a model, we would have y bar. If we do have the model, we would get to be into a y, this y hat point here. So on the next slide, I have this a little bit explained a little bit further. And so here, this is the explained variation due to the regression. So we have this line here again was y bar. This is the average of the y values. And notice that it's always a flat line because it doesn't vary by x. And y hat is this line here. This is our regression line that we talked about, the regression equation. So the difference between the predicted values and the average values is what the variation that we can explain with our regression. This difference here between the actual points and the predicted values is the error. We cannot explain this variation because it's due to error. And this variation that we have here between the average value and the actual value, this is our total variation. And y, this point here is a y minus y bar. This point here is a y bar. So this is the total variation that we have. Okay, so now we have this this relationship is that we have the total variation, the deviation between the actual and the average values, would be equal to the explained variation due to regression, or the y hat minus y bar, and the unexplained variation due to error, the actual minus the predicted values. So this is a mathematical relationship that we have here. And again, this is the total variation is explained variation due to regression plus unexplained variation due to error. So this is the total. Explained is right here and unexplained is right here. Or we can also call this the sum of squares total, SST, equals the sum of squares due to regression, SSR, and the sum of squares due to error, SSE. So SST equals SSR and SSE. Sometimes some statistical software are confusing because they could call this something else, like they could call this the explained or the residual or something like that, but this is the notation that I use. One of them is the one that you can explain with regression, and the other one is the one that we cannot explain with the regression, and it's due to error. Okay, so next I will talk about the least squares method, or the OLS, ordinary least squares. And this is a method that is used to calculate the coefficients so that the errors are as small as possible. In this case, we minimize the sum of squared residuals, or sum of u squared, and u is the actual minus the predicted values, and this is what we minimize. So when we minimize this expression here, we're looking for solutions of betas of B0 and B1. These would be the estimated coefficients here, so that the regression line passes as close as possible to all the actual values of y. So in the simple linear regression model, the coefficients would be calculated as this. B1 would be equal to the covariance of x and y divided by the variance of x. And B0, the intercept, would be equal to the average value of y bar, minus B1, the coefficients that we get here, times x bar, the average value of x. And that's how we can calculate manually by hand or by Excel the coefficients in a simple linear regression model. When we have a more complicated case here with more x variables, then we need a more sophisticated computer program such as Excel or one of the software packages in order to estimate the model and come up with the coefficients. Okay, so on this slide I have how to do an OLS regression in matrix form. So it's just a little bit more complicated, and we will use this notation when we go through the rest of the class and the materials. So the regression line is specified as the expected value of y given x, that would be x prime beta, and here we can spell out this expression as beta 0 plus beta 1 x1 and so on, plus beta p xp, where p is the number of independent variables. And if we take derivatives of this expression, say with respect to xj, so we would have dE of y dxj. If we take, say, a derivative with respect to x2, that would be exactly the coefficient b2. So in this case it would be bj if we take the derivative with respect to xj. The reason for that is that all the coefficients here and all the variables, everything enters linearly in the model. So these coefficients are linear. And that's why in this case we have that the marginal effect would be equal to the coefficients. That's why we can just look at regression outputs and we can interpret straight the coefficients and their magnitudes. We will see later on in some models, such as the probit and the logit model, that this is not always the case anymore when we have models that are not linear. So in multiple linear regression, the coefficients would be calculated as b equals x prime x inverse x prime y. And that's how these coefficients are calculated when we use software packages. I will just briefly talk about the assumptions of the OLS estimator. First, we are assuming that there is exogeneity of regressors, because if that's not the case, then we would have biased coefficients, and that's not good, and we would need to use one of the instrumental variable approaches that I have a video on. We also assume homoscedasticity, which means constant variance, and that's a very important assumption. If we have heteroscedasticity, there's some other methods that we can deal with to correct for that. And we're assuming also uncorrelated observations, which means we don't have an autocorrelation or something like that. So this is a very simple, plain vanilla kind of OLS model. So now I will talk about goodness of fit. And for that we use R squared. R squared is also called the coefficient of determination, and it provides a measure of the goodness of fit for the estimated regression equation. R squared is defined as SSR divided by SST, or 1 minus SSE divided by SST. So you can go back and recheck what these are. SSR is the sum of squared due to regression, and SSE is the sum of squared total. So we have here what we can explain with the regression versus the total variation that we have. So that's what R squared would be, the proportion of variation that we can explain with the regression in comparison to the total variation that we have. So value of R squared close to 1 would indicate a perfect fit, and values close to 0 would indicate a poor fit. And we want as high R squared as possible. Typically, R squared greater than 0.25 is considered good in the economics field, but I've seen papers published with R squared as low as even 10% or even 5%. The higher the better, but typically there's not much you can do about it once you have your data set. So the interpretation would be if R squared is equal to 0.8, then 80% of the variation would be explained by regression and the rest due to error. So that would be a good fit. Now, one of the problems that occurs with the R squared is that it always increases when a new independent variable is added. And that's because the sum of squares total would be the same, and the sum of squares error would decline, sum of squared regression would increase. Why is that the case? Because every time you add a new independent variable, it will pick up some of the variation. It just has to, regardless of how irrelevant that variable is. However, we don't want to be putting a lot of irrelevant variables in our model, and that's why it's good to use this adjusted R squared, which corrects for the number of independent variables. So here the adjusted R squared would be equal to 1 minus R squared. This is the normal R squared that we have here before, which is the SSR divided by SST. And then we have n minus 1 divided by n minus p minus 1. P is the number of independent variables and n is the number of observations. So notice what happens when p is equal to 1, right here. We would have, with one independent variable, we would have this would be almost close to each other, and it will almost cancel out, and we would have R squared. So the adjusted R squared and R squared would be very, very similar. As this p increases, we would have more and more penalty here, and the adjusted R squared would be going down and down. So we don't want to put too many variables, independent variables in the model that would pull the adjusted R squared down. So So there is a trade-off between the number of variables and the adjusted R-square. So now I will talk a little bit about the two tests for significance of coefficients. We will start with a t-test and then end with an f-test. A t-test is for the significance of one coefficient, and it is used to determine whether the relationship between y and xj is significant. So the coefficient on the independent variable sj is beta j. So the null hypothesis h0 would be that beta j equals 0, and the alternative is that beta j does not equal to 0. So the way to read this is also that the coefficient is not significantly different than 0, and here is where it's significantly different than 0. Or sometimes we say, if we fall into this case, is that the coefficient is significant, and we understand that significant means significantly different from 0. So in order to test this hypothesis, we would use the t-distribution, and the test statistic t would be equal to the coefficient divided by the standard error. And the coefficient and standard error come from the software packages when you estimate a regression model. So then you need to get critical values from the t-distribution and perform a two-tailed test. So again, this is the normal distribution or the t-distribution, and then you have, these would be the rejection areas. So we have a 5% significance level or 95% confidence level, and this would be the confidence interval. So instead of just talking about the coefficients here, they're normalized by the standard error. So if a coefficient or the t-statistic falls somewhere here, we would say, well, that's not significantly different than 0. But if it's way out here in the rejection area, we would say that the coefficient is significantly different than 0. So we have two rejection rules. They're equivalent, lead to the same conclusion. We would reject the null hypothesis, and we would conclude that the coefficient is significantly different from 0 if the test statistic is in the critical rejection zone right here. If we have a test statistic here or here, which typically means if the test statistic is above 2 or below -2. And second, if the p-value is less than 0.05. Because if we have a value here, that p-value is the area underneath the curve right here, it will be less than 0.05. So one of the goals here is to find coefficients that are significant, right? Because you don't want to have a regression where everything is insignificant, which means none of your independent variable explain the dependent variable. So you need to play around with the model until you find good independent variables that could explain your dependent variable. Okay, so this was the case about t-test for one coefficient significance. Now I will talk about an f-test for overall significance of all coefficients. And in this case, we're testing whether the relationship between y and all x variables is significant. Or you can select a subgroup of x variable and you want to test for the joint significance of those variables. So the null hypothesis is that the coefficients are jointly significantly different than 0. And the alternative is that the coefficients are jointly significantly different than 0. So I missed the word not here. So the null hypothesis is that the coefficients are not significantly different than 0. And I will correct this before I post it online. So here is the case H0. All of them are not significantly different than 0, or they're close to 0. And the alternative is that at least one of these would be significantly different from 0. Okay, so to do this Ftest, we would use the F distribution, and the test statistic F would be equal to mean squared due to regression divided by mean square error, and the critical values would come from the F distribution, and the Ftest would be an upper one-tailed test. So here's what we call an ANOVA table, And here we talk about the total variation equals to explained variation due to regression plus unexplained variation due to error. If you remember, we already talked about that during the graph, and here is this thing in a table. So here we have the source of variation. We have either due to regression, due to error, or the total variation. And these are the quantities that we talked about: SSR, SSE, and SST. So that's the difference of the actual and the average values. This is the difference between the actual and predicted values, and this is the difference between the predicted and the average values. In this case, we would have P degrees of freedom would be the number of independent variables for the regression. For the error would be n minus p minus 1, and for the total would be n minus 1, where n is the number of observations. So the mean square regression would be equal to SSR, this value, divided by P, and MSE would be equal to this one divided by this. And the F statistic would be equal to MSR divided by MSE. So that's how we come up with the F statistic. So once we have this F statistic, again, you need to look up the critical value in a table, or you need to look at the p-value for that test, and that will tell you our conclusion. So if you look it up in the table, the critical values, you will need to look up with degrees of freedom in the numerator p and degrees of freedom in the denominator n minus p minus 1. And the conclusion would be that we would reject the null hypothesis if the F statistic is greater than the F critical value, and we would reject the null hypothesis if the p-value is less than 0.05. So again, if we have this is how the F distribution would look like, we want test statistic that is way out there in the rejection region. And the goal here is to find regression model with coefficients that are jointly significant, because this would mean we have a very good model that could explain a lot of the variation in the dependent variable. Okay, so this was how to do linear regression models, including the simple and the multiple regression models, and how to do how to calculate the coefficients and how to do significant tests. So after this video, I have another video with an example, and then I will proceed to talk about how to estimate these models using software packages Stata, R, and SAS. So please join me to watch the rest of the movies.